Our next numerical method for solving equation, called fixed point iteration, or sometimes just FPI, is based on the idea of a fixed point. So if we start with a function, then its fixed points are the values p, where f of p is equal to p. So geometrically, using my function here as an example, we're looking for the point where the graph of our function crosses the graph of y equals x. Now, when we've got a specific function like this one, calculating the location of a fixed point means solving the equation f of x equals x. So with this function, that would be x squared minus 2x plus 2 equals x. And that's just a polynomial equation. We can solve that pretty quickly. We'll set it equal to 0. X squared minus 3x plus 2 equals 0. When that factors, it's x minus 2 times x minus 1, and we get two solutions, x equals 1 and x equals 2. Now you can confirm we've got the right values pretty easily just by going back and evaluating the original function at those values, right? F of 1 is 1 squared minus 2 times 1 plus 2, which is 1, and f of 2 is 2 squared minus 2 times 2 plus 2, which is 2. And that's exactly what we want from a fixed point. The number we put in is the same as the number we got out. And this also matches what we're seeing over here in the graphical representation, where those crossing points do appear to be at x equals 1 and at x equals 2. So suppose we start with that same function and evaluate it at 0.5. Right? That gives us f of 0.5, which is 1.25. Right, now let's do it again. Let's take this x value and make it the new y value. Well, f of 1.25 is 1.0625. Right, so let's do it again. Right, I'm going to make that the x value, and if we put that into the function, we get 1.003906. And if we do it one more time, I've got everything written out neatly here. If we do it one more time, we get 1.000015. Notice the pattern here. As the process went on, the sequence of values seems to be approaching that fixed point that we identified on the last slide at x equals 1. Right, well, suppose we try this again, right? But let's do it on the other side of 1. Okay, let's do this with x equals 1.5. That's halfway between the two fixed points that we found at 1 and 2. Well, if you work through the iterations, just like I did here, it looks like the sequence is once again approaching 1. Okay, so suppose we go even closer to 2, right? And start with x equals 1.75. Well, if we do the same iterative process, we get the same thing. The sequence is still approaching that left-hand fixed point at 1. All right, so let's go the other way, right? Suppose we go all the way over to the other side of 2 and pick something that's really close to 2. Let's say we start at 2.01, right? If we do that, not only does the sequence not appear to be converging to 2, it actually appears to be moving away from 2, right? It appears to be diverging. So to kind of try to get an idea of what's going on here, let's go back to the graphical version, right? So on the left-hand side, I want to look at what happens when we start at x equals 0.5, right? Well, when x equals 0.5, we get that y value. It was at 1.25. All right, so that's the value that I want to put into the function next. So I'm going to go over to the y equals x line, right? Because that's if y is equal to 1.25, then x is equal to 1.25. So if I go from there down to the function, I get my new function value that was 1.06 something, I think. Go over to the y-axis to y equals x again. Now one more time we'll do this. We'll go down to the function, and hopefully you're starting to see what's going on. right? These iterations are kind of spiraling in towards that fixed point that we identified here at 1. All right, well, what happens on the other side? Right? What happens with 2? Well, if we start, say, over on the right-hand side of 2, somewhere around 2.5, right, we go up to the function. And then to get our next height, I'm going to go over to that line y equals x, right? And so that gives me, I'm now in the right x position. If we go from there up to the function, then I'll go over again, and now hopefully again you see what's happening, right? In this case, these iterations are moving us further and further out. They're moving us further and further away from the fixed point down here at x equals 2. So this has given us quite a bit to think about. First, we've seen that some fixed points are attracting. That's actually what they're called. They're called attracting fixed points within some neighborhood around the fixed point. But we also saw that those neighborhoods can be finite. And we've also seen that sometimes those neighborhoods don't exist at all. Sometimes we get fixed points that are repelling, and that is in fact what they're called. They're called repelling fixed points. In the next lecture, we're going to look at the relationship between solving an equation questions and find a fixed point questions. And we'll see how we can rewrite an equation as an equivalent fixed point problem, often in multiple ways, and what some of the consequences of those choices are.